Center for Urban Studies, and I welcome you to the first of our transportation seminars this quarter. And I'm standing in for my colleagues as well. Rob Bertini is on jury duty, and Chris Monsieur is at a meeting, but maybe both will arrive later on. Before I introduce our speaker, I also want to give an announcement for an event coming up here in Portland, the fourth Oregon Symposium on Integrated Land Use Transport Models. So I have a flyer for that for people who are in the room, and for people who may be watching us on the web, you can find that on the ODOT website. And another reminder, we are webcasting the seminar, which means we are recording questions and answers. And so when you ask a question, we ask that you use the microphone. There hopefully is one near everyone. You need to hold down on the touch area. Keep the red light on as you're speaking so the people watching on the web can hear the question as well as the answer. So without further ado, I am very pleased to announce this is one of our special seminars. We have Doug Hunt, who is with the Institute for Advanced Policy Research at the University of Calgary. He's also a professor there in civil engineering. We're happy to have him here. And today he's going to be talking about a specific aspect of transportation modeling that's dealing with commercial vehicles. I'm going to turn it over to you.
Great. Thank you very much, Jennifer. Pleasure to be here. Lunchtime today. I think without further ado, we'll just get going. I've been told I have about an hour, so I'll try and move through things so that we finish with maybe a few minutes to spare if anybody has some questions. When Rob Bertini asked me to give a presentation to the group, I thought something that would be interesting that highlights something that's a bit different than some of you who have been working with me on some things used to me working in land use transport modeling. This is a somewhat different area of work that I've been involved in as well. So I thought it would be a bit sort of interesting to extend into sort of a somewhat different area than you've normally heard me talking about. What it is a microsimulation of urban commercial movements using a tour-based framework, looking at the individual commercial movements, developing a model that can be used, is being used now in policy analysis for the city of Calgary. What do I mean by commercial vehicle movements? These are vehicles being operated for commercial purposes. This is a fairly inclusive term. It's sort of everything that isn't being done by households for personal matters. So this includes things that are being done by government, not-for-profit activities, as well as all of the things that would be done by sort of business firms in the area. This, from the literature we know, and this is confirmed in the statistics we got from our work, this comprises about 10 to 15% of the total urban traffic. The remaining 85 to 90% is the household category of vehicle movements. So just some examples of what we're talking about here on the commercial side. This does include the large trucks carrying goods, but it goes beyond that. It also includes service workers going around to do things for clients, such as electricians and plumbers, people going to sales meetings as part of their business activities, the delivery of mail, the delivery of parcels. All of these different things are included in what we're calling commercial movements for today's presentation. We were given a remit by the City of Calgary. They wanted to develop a model, and they wanted it to be, first of all, policy sensitive. They wanted to be able to look at changing what are called the truck routes system, which is really a series of restrictions on what types of trucks can move on certain types of arterial roadways in the City of Calgary. Looking at how, if they influenced operating costs and the related taxes for vehicle movements for commercial purposes, how that would influence behavior, and also how changes in their land use zoning might influence the demand. They also wanted it to be accurate. in terms of its responsiveness to policy and also have a reasonable amount of what they called fidelity, reproducing what goes on in the real world. And also, they wanted it to fit within the data requirements we already had for running the regional household travel model at the City of Calgary. So it had to fit with that household travel model, not really have any new data requirements for running things into the future. So just a little bit on the work actually involved not only the City of Calgary, but the City of Edmonton as well. We finished the model in Calgary, and we are just finishing the model in Edmonton. I'll be describing what we've got for Calgary, but I thought it would be useful just to give you a bit of background of those two other cities relative to Portland. I'm showing you the city and the metropolitan populations in both of those cities in Alberta relative to Portland there in the blue. You can see they're slightly smaller, but similar sort of cities in magnitude. In terms of some of the travel behavior, comparing Edmonton, Calgary, and Portland through time a little bit. The Edmonton result numbers are for 1994, as well as Portland and Calgary is 2000. But you can see fairly similar sorts of travel behavior. These are two sort of Western Canadian cities, roughly the same kind of magnitude, so you get roughly the same kinds of travel behavior. Here's an example of the mode split. Slightly larger emphasis on the automobile in Portland than there is in Calgary and Edmonton. Now, what we did is develop a tour-based microsimulation. That's a rather jargony term. I'd like to talk a little bit now about what we're talking about with that. This considers the tours made by commercial vehicles out from their establishment base, rather than the individual trips that they're making. It connects these tours together. And what we're doing is a microsimulation of each of those tours using Monte Carlo techniques, and I'll spend a couple of minutes describing what those are. And we're using disaggregate choice-based models to come up with the sampling distributions to assign the attributes at each of the different points in that microsimulation. This makes the model, we would argue, behavioral, in that there are behavioral models that are changing those sampling distributions. When we do this, we're able to use a bunch of information that isn't typically available when you're doing a trip-based style model. We can look at the full tour's conditions influencing some of the decisions that are made. We know the location of the establishment is the tour base. Eventually, the tour has to return there again. So that gives us some fixedness in space that we sometimes don't have. We can pick up, because we're keeping track of what is happening by the clock as well, we can tell when we're getting close to noon time and whether the driver is now going to stop and have lunch. We can also see when it's getting close to 5 o'clock, potentially, when the shift is going to end, and there's a much greater propensity for him then to return to the establishment. So we can pick up those kinds of work shift influences explicitly. And what we will be doing is we will simulate each trip as the tour starts out from the establishment point and goes around and makes the stops, eventually returning to the establishment again. We would argue this is closer to the reality that goes on in that they make tours like this. It's not a successful business that's going to be sending somebody out to a client, then back, and out to a client, then back, and out to a client, then back. That's going to have higher transportation costs than being able to organize visits to a number of clients in a tour. So we would expect, all right, the competitive advantage would accrue to the ones that are better able to organize. So we would expect to see these kinds of tours in theory, and so we went out, expecting to get that kind of data when we collected it. So just to show, an establishment with clients is not going, it's sending some sort of shipment of a good or a service to these clients. All right, and we're going to pick up then what's happening in terms of that entire tour, visiting one client to the next before returning to the establishment. And this is what we call a tour that then is being made. And it's called a work-based or establishment-based tour because the start and end point, the way we've defined things, is the establishment itself. Now, one of the characteristics we found when we went out and got the data was that, this is the sort of the bottom point in the set here, there is a relatively large number of stops in a lot of cases. We found an average of a little over 5.5 stops per tour. That is much larger than the average number of stops per tour on the household side of this kind of modeling. And there isn't really a readily apparent hierarchy in the same way there is with household travel, where if there's a stop for work, then we sort of say, well, that's a work-related tour. That's what we call the primary destination. And then we can have intermediate stops. We don't have that same sort of hierarchy available to us, so we had to work with a different sort of approach we felt was more appropriate in the growing of the tours that we look at. And so we call this growing rather than rubber banding in the nature of the way we build up tours. So let me just describe, right? This would be what I call a rubber banding process for a standard household style microsimulation of a tour. All right, we have the home, and then we have the primary stop. If it's work, that's clearly apparent, or it may be a school tour that's being made, so the school location is the primary stop. And sometimes, in order to fit other types of tours as well in, it may be the most distant stop in a series of shopping stops that are made as well. But in some sort of way, rules are imposed on people's behavior, defining what that primary stop would be. And then there's a consideration of the attributes of a tour that goes back and forth between that primary stop. Tour mode choice can now be done concerning what the attributes are for that particular interchange back and forth from the primary stop. After that's done, there is then some consideration of the potential for intermediate stops. And I call this rubber banding because it's like stretching a rubber band between the 2 points and then seeing if you want to stretch it these ways as well, laterally. And so the decision is then made whether or not to include 1 or 2 intermediate stops. So we would have 3 stops as the number of stops occurring on this particular tour. The idea with growing tours is that we want to avoid that hierarchy where we have to define a primary stop, and instead we say after the initial first stop and where that's located, we then have a decision process: do we make another stop, or do we return back to the home or the establishment location again? In this case, the answer is we make another stop, but then at that point, we then have another consideration of whether we return or we continue on with our tour. And in that way, we grow the tour, right, instead of that rubber banding process, and eventually returning back to the home. This way, we can have, in a natural way, a much larger tour with many more stops occurring, and there isn't one that has to be a primary stop in it. Right, the data that we had available to us, the 2 cities of Edmonton and Calgary went together with the province of Alberta to do a commercial movement survey. And this was very much like a household travel survey, where you go into people's households and ask them what they do over their assigned travel day. In this case, we went to different business establishments, and we asked them what they did over their entire assigned travel day, and got all the information for all of the vehicles that left on that particular day and eventually returned again. This was all commercial movements being made by all establishments, not just freight movements, not just trucks. In the end, we went to 3,100 establishments in Calgary and another 4,300 establishments in Edmonton. The total cost was about $1.5 million Canadian dollars for the entire data collection effort. So just a few aggregate statistics on what we found. We found something that conformed very closely with what we saw in the literature about that 10 to 15% rule. We were finding that commercial vehicle movements were about 12% of the total. The remaining 88% are personal movements. That actually compares fairly close to just the home-to-work segment of the household travel. So it just gives you sort of a sense of the order of magnitude that we're talking about for modeling commercial movements in an urban area. This is the distribution of the tours being made by the different kinds of establishments in the different industries that we looked at. You can see transportation handling. These are the folks who actually run trucks, with the business of going to places, picking up things, and taking them to somewhere else. They provide the service of handling goods. All right, those are where trucking companies fit. They're about 22% of the commercial movement tours that are being made. Retail is another 13%, wholesale another 9%. Private services, again, in a sort of Western urban economy, we'd expect, services are a very large portion of the total economic activity, and that's reflected in roughly 36% of the commercial movements being made, fit within that particular category. The thing to take out of this, the big message out of this, is if you focus just on the movements of trucks, all right, that are doing transportation handling, you are missing a huge amount of what's actually going on in your urban area in terms of commercial movements. It's not good enough just to go to the trucking firms. We broke down into 3 vehicle types for the microsimulation work that we did. Light vehicles. This is anything with 4 wheels, including automobiles, vans, and sort of what we would call pickup trucks. You use the same term here, pickups, right? Single unit trucks have 6 wheels. This is medium. And then what we call heavy is everything with more than 6 wheels, and things with tractor-trailer units in particular. The reason we went to this is, first of all, the truck route policy that we were supposed to be able to simulate the impacts of, it differentiates on this basis. So we had to pick up on that, represent in those particular categories. The much larger heavy vehicles have a much larger impact, both in terms of what we call their passenger car equivalents, when they're loading, when we're looking at the congestion on the networks. And also, they actually are the ones that do the damage in terms of pavement loads that are substantial enough to actually impact the pavement itself. They have different emission rates, and in our calculation of emissions, we use different rates for these 3 different vehicle categories as well. What we found in the commercial fleet that was being used was about 60% light vehicles, another 30% roughly medium vehicles, and perhaps about 10% heavy vehicles in an urban context. Okay. Looking at the stop purposes for which things are occurring, it was about 66%, about 2/3 for services, the delivery of services, and about 1/3 for the delivery of goods in the urban area. Now, that includes the special category of that transportation and handling. They're a funny group, or a special group. They actually provide the service of handling goods. So they're sort of halfway in between the two, if you will. The other category, the blue, these are own account handling of goods. So if I run a flower shop and I hire somebody and operate a van and I pay for that van on my own account, it goes in the blue category there. If I have a flower shop and I call up FedEx to have them deliver the flowers everywhere in my market area, then I actually fall into, it's FedEx doing the work, and they fall into the orange category there. Okay. We would trace then the FedEx truck from the FedEx depot moving around and making all of the stops on its tour, including the picking up and dropping off of things, including picking up my flowers and taking them somewhere to perhaps be handled further. There may be another tour that they generate from a depot where they then take it to where they may do consolidation and redistribution. That's all included in the tours that they're making. Right? Whereas if I'm operating the vehicle on my own, all right, own account, there's going to be the van leaving my shop and making a series of stops in a tour and eventually returning to my shop again. All right, so I just want to reinforce that transport and handling. All right, if I'm client A, I have a flower order and I'm sending that to client B. In terms of the transport and handling, there's an establishment that's making a tour. It has a series of other clients as well, and the red dash line is where the good, my flowers, is actually moving, but the tour that we're modeling, what we're picking up, is the provision of that entire service by the transportation and handling establishment as part of their organization of all of those kinds of pick-up and drop-offs that they're making. I also want to cover the different stop purposes. We can have going to clients to provide a service or pick up or drop off a good, but also people can stop, the drivers could stop for other reasons, including lunch. Right? There's a range of other different purposes. And then another category we had is return to establishment. So we can talk about stopping to deliver goods or service, stopping for some other purpose, or stopping in the return to the establishment as the next stop purpose. So there's the definition of the goods, the service. The other, this can include vehicle repair or fueling, personal stops for the driver, and stops for other indirect business purposes. There may be a driver sent out to go to the bank to put in payroll or something like that. The return is always the return to the establishment. It's the last stop of a tour. And this is the rough breakdown then of what we saw for the entire sample, expanded, of course, for the stop purposes. All right, now in the modeling, how did we represent that? The first thing we had to tackle was we had to represent the truck route policy that the City of Calgary has. And we have to do that within our assignment of the commercial vehicles to the road network. We have a generalized cost with both time and distance components and coefficients that weight between those two. And then the assignment process identifies potential routes using that generalized cost value to build alternative routes through the network. What we wanted to represent in terms of the truck route policy, it's okay to use the designated truck roads as much as they want, but then if they have to get to a particular origin and a particular destination, they must minimize the distance they spend off of that truck route system. All right, so what we did is we developed a path choice algorithm where we added a synthetic 100-minute penalty for each 50 meters of length on those non-truck roads. And then we would use that generalized cost with that additional penalty to do the path search. We would do the allocation on that basis, but then we could strip out the penalty to do the calculation of the actual times and costs, to calculate what the drivers were really facing in terms of the times and cost values. So just an illustration of that, if I have an origin to destination that I'm considering alternative routes for, and those are the truck routes in orange where drivers are permitted to drive as much as they want, but they must minimize their distance on the other links. If we had those particular disutility values and we allowed just a standard minimum path process to work without the penalties, they would end up driving in the pink parts far more than they should at the destination end. So what we had to do was have in addition the lengths of those links, and then on that basis put penalties of additional 100 minutes for each 50 meters or portions thereof, and then have the assignment algorithm do the minimum path through that, and it would come up then with the legally appropriate route assignment on the destination end. But then after we're done with that, we can then strip out using the formula shown at the bottom, and we come up with the 8.1 minutes of disutility is the actual time that they would suffer on the network. So we had to build that up and get that working, and that does work fairly well. In the microsimulation itself, I wanted to talk a little bit about the mechanics of determining the states, spend a few minutes on that. As I said, we use Monte Carlo selection, and when we have discrete attributes that we're assigning for the tours, we use choice models with the sampling distributions. And then when we have continuous attributes, this is for the durations. One of the things we have to do in establishing that entire tour and how it's going over the whole day is we have to say how long they spend at each of the stops that they're making, and then advance the clock to keep track of what time it is. So that if we see we're getting close to lunch, there's a much greater likelihood the next stop will be a stop for lunch, for example. And we used hazard duration models to establish the sampling distributions for those Monte Carlo processes. And then I'll talk about the process for the commercial movement tours as well, go through the actual mechanics. But I'll talk about this first and just say, if I have some sort of point where the driver has 4 alternatives, there may be 4 stop alternatives, there may be 4 stop purposes that we're trying to allocate, and I've just listed them as A, B, C, D. And I can have what I hope is familiar to some of you is a formula of the logit model, all right, that will have a utility associated with each of those alternatives, and I can put whatever I would like in the development of the model for things that influence the driver's decision among those 4 possibilities in my little logit model, and it will then assign probabilities for those 4 alternatives, and I can represent that on the y-axis of the diagram there, the 4 probabilities between, they add up to 1, and then I can do a random number generation, and just a standard uniform distribution for the random number generation on the x-axis there. Whatever I come up with, I then translate over to be the value. In this particular case, we would say the driver, in this case, chooses B. All right, so that's the decision in this particular case. All right, and then I would move on to the next situation where I have to have the driver do the next thing within his larger tour, and I will have another logit model and another set of alternatives, and I will run the microsimulation again for that. At the individual level for one driver, I'm pretty certain I'll have got it wrong for that driver. Okay, but when I do it over a large number and add it all up, my large number properties take over, and I start to get a representation of the patterns overall that's quite respectable. Okay. Then for durations, that's the other thing. How long is a driver going to spend at a particular stop? All right, it's just a different sort of sampling distribution I have to work with. I've got observations from my data of how long they tend to spend at different kinds of stops. And I can then look at the cumulative distribution function of that. All right, and I do my same random number generation. It will then give me a particular value. In this case, I've hit the value t. All right. The cumulative distribution is just the percentage having a value less than that duration. All right. The percentage having a value less than that duration. So in this case, it would be a duration t. All right, so those are the basic mechanics that we use, and I'll sort of talk about the kinds of whether we're using Monte Carlo, whether we're using a behavioral model and what the behavioral model looks like, a logit model, or whether it's a hazard duration model at each of the different points. All right, the process we went through overall, and we'll go through this in some detail, but just hitting it in the highlights right now, is we looked at the aggregate number of tours for each zone that would be coming up. We would look at each zone in the model, and we run the model to come up with a number of tours that are being generated by the businesses, establishments that are located in that zone. And it might come up with 34 tours. Then we allocate them to within 5 different start time periods that we had. And we had sort of pre-AM peak, then AM peak, then middle of the day, then PM peak, and then after that, all right, after the PM peak. And we used a logit model to take those 34 tours we had generated in total, and we allocated them among those 5 time periods. So we may end up with 7 tours starting in that early time period, then another 11 tours starting in the AM peak, and a further 13 tours starting in the midday. Once I've got those values, I then create a list from those. So I have 13 slots associated with that value of 13 tours. And what I have to do in the microsimulation is come up with the attributes that are consistent with, that fit for that particular set of 13 tours. So I consider the first tour, I fill in all the attributes for it. How many stops does it make? What type of vehicle does it use? All right, using that microsimulation process. And the things I have to pick up are the purpose of the tour. We'll talk about the categories. The vehicle type that was used. The specific start time down to the minute. And the stop attributes, the purpose for each stop, the location for each stop, and the duration at each stop. All right, and then eventually returning to the establishment again. And I get my behavioral response then in my microsimulation because it's changes in the choice and the duration models that we're using for the sampling distributions to come up with those attribute values. All right, so this is a diagram of the process I just described there as sort of a flow chart. And that is iterative down there until we return to the establishment again. That's the growing process. Right? So this is what we go through. The first one is to come up with the number of tours. Then we consider each tour in a list. We look first at the vehicle and tour purpose. We have to assign a vehicle type and a tour purpose type. And then we assign a tour start time. And then we go through the process of assigning where the vehicle stops, right, what it does when it stops there, and how long it spends in doing that. Until the tour is finished. When we finish that, we go on to the next tour in the list. So looking at the tour generation, all right, I won't spend a lot of time on this, but just to give you some of the nuts and bolts about it as a list, we used an exponential regression to represent the number of tours generated per employee per day at a zonal level. We have about 1,400 zones for the entire Calgary model. So this is how we mesh together with an aggregate form of model. We look at the zonal information that is there in terms of population and employment by the different industry categories. And then we have a series of exponential regression equations to come up with the average number of tours per employee based on a number of different things that are listed there. The land use type, which is a proxy for occupations. All right? If I have an industry, a firm that's an industrial firm, but they're located in downtown Calgary, all right, where there's a lot of high-density office towers, it's likely they're white-collar workers in that particular industry. They're going to have a very different rate at which they generate commercial movements and different types of commercial movements than if it's a factory out on the edge of the city in one of the industrial areas. Right, so that's why we use land use as a proxy for occupations, consistent with the data that the City of Calgary already had in their aggregate model for households. We use accessibilities to population and employment. And the first thing that we found when we threw these accessibilities, one of the standard things is when accessibilities go up and it's easier to travel to get to more places, households tend to travel more, because it's easy to do and there's a lot of sort of the benefits are there then, the costs are lower, so the benefit to cost ratio is there. All right? Well, if you think about it, firms are doing a different kind of thing, at least in the short run. They have a certain amount of services or goods they have to deliver to their clients. All right? If it's really, really easy to get around, if the accessibility is high, they're going to do it with fewer trucks. And as things get more congested and their clients get further away and the accessibilities are getting worse, they're actually going to have to put more on the road in order to satisfy their clients' needs. So we do expect, if we think about it, a negative sign rather than a positive sign. It's the dual of the households problem, for those of you that do OR type operations research work. All right? So we are quite comfortable with getting negative signs for this as opposed to getting positive signs for households. That has implications for evaluation. We actually have to look at the producer surplus rather than the consumer surplus when we do the evaluation of the benefits to firms of transportation policy. We also have the proportion of workers in a given industry that we found to be an aggregate variable that did some significant jobs in explaining the number of tours per employee. All right. Then after we got that aggregate number, we used an aggregate level logit model to allocate the tours over the whole day from that zone to the different time periods. And here are the 5 different time periods we looked at. And these are consistent with the 24 hours split into 5 periods that's done with the aggregate model for the households that we have in Calgary. Then the tour start time. This is where we're doing a this is still the allocation among those 5 time periods. Here are the attributes in the utility functions. We tried to put a bunch of different types of things in. We squeezed things and pushed them, and we got some accessibilities that had some coefficients that made sense. We expect them to be positive here at this point. Really, to a large extent, the job was done by the alternative specific constants. There's a fairly fixed pattern that didn't vary much across space in the allocation of tours by a given industry to the different time periods that they tend to start out at. There tends to be sort of they use the work day and the work shifts to organize things rather than a great deal of response to congestion or other factors. So while we would have perhaps liked a bit more things explaining that distribution other than just the constants, we sort of had to live with that. Now we get into the microsimulation component. We have a list of the number of tours coming out of a zone by each of the 5 different industry categories that we were looking at that I showed previously. We now have to assign a vehicle type and a tour purpose. And we tested nested structures, and none of them were justified statistically, empirically. So we ended up with allocating both the type of vehicle, about those 3 vehicle types, and the purpose of the tour overall, and we'll talk about what that meant in a little bit, between service, goods, other, light, medium, and heavy. So there were 9 possibilities. And here's where we had one of those logit models with the different utility functions, and we would assign those a priori distributions of the probabilities that we would sample from, all right, in order to get the specific attribute. Which particular of these 9 here, depending on what the logit model assigned to the probabilities, and when we rolled the dice, figuratively, which one of the 9 we hit as a result. Okay, and the things that influenced those probabilities were the land use type, the error was in, picking up whether it was blue-collar or white-collar occupations, the accessibilities, so we have transportation influences on what the vehicle type would be. If it was very easy to get heavy vehicles around, there was a higher propensity to use heavy vehicles. Maybe if there was the truck route policy was such that it was easy to get out of there was a high density of truck routes, that tended to encourage more use of larger trucks at this particular point. So we saw positive coefficients there. Proportions of the workers by industry, and again the alternative specific constants. Then on the tour start time, here's where we just used a fairly simple observed distribution of what those are. Eventually, I would like to see us replace this with something that's a bit more responds to different things. But at this point, it's just what's called an observed sampling distribution, and we just randomly select from that the probability. Between 0 and 1, we generate a random number, and then we hit the particular time here. This is for starting between 7 a.m. and 9 a.m. For the a.m., that's the a.m. time, 7 a.m. to 9 a.m., for industrial tours being made by industrial establishments. You can see there is a slight tendency. It gets flatter. That means there's a much larger range where you would have people leaving right around 8 a.m., you can see. So there's a peaking that's going on with the tours starting 8 a.m. or a little bit after 8 a.m. That's probably because the work shift is starting at that point. Okay. All right, now we work then talking about the iterative process. We've got this vehicle. We know the vehicle type. We know the purpose of the tour. We know the zone they're leaving from, and we have a start time, maybe 7:12 in the morning. Now we're going to say, all right, what are you going to do at your next stop? And then where is that next stop going to be? And how long are you going to spend there before you think now about what are you going to do for the next stop after that? We're going to grow our tour. We had to then organize, we wanted to have a series of different models assigning the probabilities for the Monte Carlo process, trying to group together different types of tours being made, hopefully getting ones that had similar sorts of sensitivities so that the attributes were representing sort of a group or a market segment, if you will. So we have the tour purpose and the vehicle type as the two things distinguishing. You can see 5 different tour purposes. Down here, services, goods, or other as the tour type. The vehicle type is light, medium, or heavy. And the type of industry that the firm is in, with those 5 basic categories, again, that I described earlier. And so we have a little 3-letter designation. You can see R-S-LMH. It's indicating that these are tours being made by retail firms for delivery of services, and all types of vehicles are included in that. So all of the models then that we developed for assigning the probabilities, the logit choice models, there's one for each of these 13 different segments that we worked in. All right, so, and they're indicated in those where the different segments are. All right, so first of all, on the next stop, purpose. All right, they can make a goods stop, a service stop, an other stop, or a return to base with some restrictions. All right, you can't make a goods stop if you're making a service tour. Remember, we assigned a tour earlier. We found very, very few cases. I think we actually found 5 observations where a tour included both what we called a goods stop and a service stop in it. All right, so we were able to say we'll just cut out those 5 and really say we just ignore that very, very small frequency. We were able to simplify things then by saying, all right, if they make a service tour, they can make service stops, other stops, or return to base stops, but they can't make a goods stop. Similarly, all right, if they're making a goods tour, the options available to them in terms of stops are goods stops, other stops, and return to base stops. And furthermore, if it's the first stop on their tour, it can't be a return to base. They got to get out and go and do something, okay, to start out. Make that first stop somewhere else, and then it's possible to return as one of the possibilities to the establishment again. All right, and what are the things that we had in our utility function for the logit model that assigns the probabilities to those different possibilities before we do the Monte Carlo? The elapsed total time since the start of the tour, the elapsed total travel time since the start of the tour. All right, if they'd spent a lot of time away from the establishment to that point, there was a certain probability influencing what the next thing they would do. And if they spent a lot of that time actually traveling, that had a different sensitivity to it, significantly different, so we had both influences included there. The number of stops by the type since the start of the tour, the time period they were in, the accessibilities for the current stop location. If where they were was highly accessible to a lot of things, there was a greater propensity to go and make another stop first before returning to the establishment. The generalized cost for the vehicle trip to the return to establishment. So they sort of kept one eye on how close they were to going back. And if they were close, there was a greater propensity, well, maybe I'll go back to the shop for lunch type of thing. Okay, that was an influence we picked up as well as the alternative specific constants. All right, I don't want to go into the details. We actually have a published paper that shows all of these numbers, but the point is we had to estimate the parameter values for all of those influences within the utility functions. And it includes, you can see, the ones where they were, the t-ratio was less than 1.96, so not as significant as we would entirely like, but still not too bad, where the darker squares are. The lighter squares are quite a respectable t-ratio, but not as large as 3.29 in absolute magnitude. The other ones that are clear all had t-ratios greater than 3.29, which are very high, very good statistics in terms of the variances in our estimators. So we had quite high confidence in the coefficients that we're getting. Right. Then the next stop purpose, we've now said they're going to make another stop. They're going somewhere. It isn't back to the establishment. We know where they would be going in that case, but if it's not, they're going out to make another goods stop on a goods tour. We now have to assign a zone for that. And essentially, the set of possibilities is the full set of 1,447 model zones in the entire model area. Then the utility for each of those alternative zones, to assign a probability for each of those, includes these attributes in the utility function. So this is, again, our behavioral component in the model, what we're picking up the influences of on the behavior of people, the commercial tours. The generalized cost for the vehicle trip to a potential stop location, so how far they were from it in terms of a generalized cost. All right. The generalized cost for the vehicle trip to return to the establishment from that potential location. So again, I know base is over here. I'm going to tend to, in my tours, stick around the base. There'll be a lower likelihood of me heading off somewhere else more and more distant from it. All right? It's really representing the market sort of areas for different establishments that they would have, tending to stick within those markets and serve clients within those markets, within the urban area. Population and employment accessibilities. There was also a sense that there's a greater likelihood to go to places where it was also easier to get to other places. They're lumping their stops together in a tour that sort of makes sense, all right? And that's picking up that particular influence in the patterns overall. Land use type, all right? Again, picking up the nature of the occupations that they would be serving, going to places. Average incomes for the households at potential stops. Some of what's going on for some of these is they're delivering things to households. Higher income households tend to buy more stuff, so they need to have more commercial visits made to their homes. So there's a positive influence of income that we pick up. Population and employment size terms. I mean, we're dealing with zones here. If there's nothing in a zone, we want to have a negative infinity utility associated with going to that particular zone, and we use a size term with logarithm functions to represent that, and we have to estimate what the coefficients are associated with that. And then this enclosed angle, this is really a much more sort of geographic or spatial representation. All the other things aside that we represented, this is really sort of picking up the spatial perceptions of the drivers and then the resulting patterns. What we're saying here is when you're at your current stop and you know your establishment indicated here, there's an angle then, an interior angle to where the next stop might be. And that angle, there can be a coefficient to say what the propensity is to tend to zip back towards the establishment as opposed to tend to sort of have a more looping style of pattern. Now, we turn that off when you start out at the start of the tour. It's not defined, and that's all I'm saying with that bit of math at the top, upper right-hand corner. But here are the estimation results for these. Again, I don't want to spend a lot of time, but you can see we get fairly good results again. Sometimes positive, sometimes negative influences for different things in some cases, but generally where we expect positive influences for a utility, the generalized cost, it was a negative utility for something being further away, so we expect a positive coefficient there, and that's what we got. We got, well, I think there's a large number. For those of you that are interested, you can look through the details, but this picking up the influence of that angle coefficient, if that tended to be positive, there was a propensity to get closer to 180 degrees in where the next stop would be, so that tended to result in a more looping style pattern. Whereas when we got a more negative coefficient with that, that was really forcing them to try and be pretty close to zero in the angle. This is really tracing out then a much more zigzag pattern, all other things being equal. My hypothesis on this, I haven't tested it too much, is this has to do with how much they can organize their tour as opposed to respond to things that come up. It may be sort of a pizza delivery job on the left-hand side there, a little bit more sort of rushing to where the next order needs to be delivered in some sort of order of when they got them, as opposed to here's somebody who has much greater freedom in ordering the pattern and maybe then tends to think in that sort of way rather than zigzagging a bit more. It's just a hypothesis, but we saw statistically significant different kinds of influences for that angle coefficient for different types of industries tours. All right. I won't go through this in detail, but I actually number crunch through an example. This is for a wholesale tour, delivering services, all the different vehicle types included, that particular segment in those 13 segments that we looked at. And doing the calculation and just summarizing some of the different effects then we pick up on this location utility. All right. Commercial vehicles are travel cost averse. They're attracted to population and employment. They prefer industrial land use to anything else. They tend to stay closer to the establishment. Right? They tend to work around it. They're attracted to areas of higher income. And for the most part, we saw a positive coefficient for that angle measure. They tend to travel in looping patterns away from their base more than anything else. All right, and the stop duration. All right, this is a plot. This is an earlier version. We were just using a sampling distribution again. You can see we have very, very large numbers of observations, so we got a very nice fit line that we're plotting for that cumulative distribution for the time. It's hours on the y-axis here. And this is for private services, delivering services in light vehicles. All right, well, you do all that nice estimation, you get a lot of coefficients that sort of tell you things about the nature of behavior, but you have to throw all of that into the microsimulation, simulate for the whole population and employment for the entire model area, and then you have to compare it with, how well are you doing in terms of matching some of the things you know. And you have to wade in and adjust, and you adjust those alternative specific constants to get it to fit what you know from aggregate observations. So these are the sorts of aggregate targets that we work towards. The number of trips per tour. We had aggregate information for the entire data set. We had to then go in and calibrate our microsimulation to reproduce those. The number of tours by vehicle type and tour purpose. The number of stops by commercial model segment. The stop locations by vehicle type and geographic sector in large geographic areas for the whole city. Then some of the intra-sector trips by vehicle types, and the screen line crossings by time period. And I have some plots just to show you. For each subsequent run, we had adjustments then to what the constants were to bring them into match. And this one is just showing, this is the aggregate number of trips per tour by each of those 13 different segments. You can see they're represented with different colors, and sort of the percentage difference between the target we were after and what the model was doing, and how we were progressing with each subsequent run and readjustment to closer and closer to values that matched what we were after in terms of targets. And this represents the proportions of tours by purpose and vehicle type, the same sort of convergence. This is the sum of the absolute percentages of differences. We want to get that down close to 0. And this is just by the 5 industry types, right? Looking at the proportions of tour by purpose and vehicle type. That was higher up in the sort of sequence of microsimulation steps I described. The total number of stops by commercial model sector. This is kind of interesting because it shows, this is for the 13 different segments of the model again. This is the number of stops that the model started out with in the white color versus the target, which is the purple color. So you can see we were off by quite a bit to begin with. But as we then adjusted the alternative specific constant associated with the return to establishment alternative, we're able to bring those down and get the blue value, which is where the model is now, relative to the target. And you can see, we can get a very close match on this by adjusting those constants. Then looking at the split of destinations, these are different geographic areas, fairly large geographic areas for our entire model area. Where we started out is we started worrying about this in run 20. You can see in the turquoise, the target was the green, and then eventually by run 58, adjusting other things. You have to keep several balls up in the air at this point, because when you start playing with some of the parameters to do with this, you upset some of the other areas, so you have to keep returning to them as well. All right, but after about run 58, you can see we got pretty good agreement there. Similar sorts of results. The point to take with this is you now wade in again with the aggregate model running, you adjust the alternative specific constants to calibrate, and that is something you can do. All right, so just as an example of the way, this is an actual microsimulation that I took out of the model. This was in zone 340, part of the central industrial area within the city of Calgary, and this is in the AM peak. We identified that a tour would occur. That was all we had from the generation model. We have to fill in all of the attributes, essentially trace what the tour does. First thing we said is it's a light vehicle making the tour, and it's a service-style tour. That means they can't make any goods delivery stops as part of their behavior. And they got assigned a start time of 7:22 a.m. And the next stop they make is a service stop. Right? They were allowed to pick between service or other. They couldn't have a return to establishment for that first stop. And that service stop was to Zone 211. That's where the Stampede grounds are. Probably that's something you've heard about Calgary, is the Calgary Stampede. Well, they were going to do something at the Calgary Stampede grounds. And that took until 9:48 a.m. And then the next stop they make is another service stop. And they have to go to an apartment to do that. That was in Zone 209. And that took until 11:21 a.m. I mean, we increased by how long it took them to drive to that Zone 209. And then we said how long they spend at Zone 209 delivering the service that they're delivering. Well, 11:21 was starting to get kind of close to lunch. All right, so they were now assigned another stop. It was Zone 2205 that they were allocated to. I don't know if it was actually the Marathon restaurant, but that's a good restaurant in that zone, so I thought it would be probably. And they took until 12:13, so they moved things along fairly nicely, right, for that lunchtime. Remember, we have a different distribution of the durations for lunchtime, which tends to be fairly peaked, around 45 minutes to an hour. Right? And then they make another stop that's a service stop, and they have to go up and they actually cross the river up to Zone 2312. That's the North Hill Mall, is where they were allocated. That takes until 4:20. Well, that's starting to get pretty close to quitting time. All right? And so at 4:20, the next stop purpose assigned was return to establishment. All right? Then we would go on to the next tour on the list and continue on in that way. All right? So we now have to fit this in with the aggregate model of what the households are doing. So we actually have to run both of them in parallel and have information being swapped after iterations to get things consistent. And that's probably all we need to say today on that. But we're able to update the travel times and then have both of the models respect what's happening because of the increased congestion because of the travel times. Maybe one more thing to say on this. The microsimulation has a random component to it. So like I said, that we know we're not going to get it right for actually every individual vehicle, but when we add things together, we're comfortable about what we get overall. But still, when we run it one time, then we run it again, then we run it again, we can get slightly different answers overall. So the process we have to go through there is we have to run it a number of times and then take the average values that we're after. All right? This is looking for what we call the expectations for those estimator distributions that we're actually producing with our microsimulation process. And we found through trial and error, we could run it about 5 times in the time it took the aggregate household model to run through its demand calculations. And so we would then get expectations for what the vehicle trip table was for the commercial side, for light, medium, and heavy. Those mixed together with the vehicle trips from the household side, that we would then go through an iteration of assigning that, getting new travel times, and those would feed back again for another iteration where the household side did the demand side for the households again, and we would do another 5 iterations on the commercial side and take the average of them. And that until we got to a certain level of convergence, at that point we then ran the commercial vehicle 30 times rather than 5 times in order to get better estimates of what those average values were, what those expectations were. Right, so this shows what we've got for loading. This is a very reasonable looking result, plotting on the network at the City of Calgary. And I think that one of the things, this is for the light vehicles. They're allowed to go pretty well anywhere in the network, right, because they don't have the truck route restrictions. This is then compared with the heavy vehicles who do have to respect the truck route restrictions. You can see a much greater focus on the industrial areas, which are shown in gray, compared to this is the all trips, light vehicles, sorry. And then less in the CBD for the heavy vehicles. Right? The light vehicles tended to focus more in the CBD. And Very little on the non-truck routes. They can, but they have to be doing it as part of a minimum distance trip to an origin or destination. Whereas the light ones have full freedom to use the entire network. This is very much in proportion to the road hierarchy, going from freeways down to local roads. All right? We are using this in practical policy work at the City of Calgary now. The household side model and the commercial movement model I've described here are merged together, and we do run policy looking at things. I've got some demonstration policy results here. They're still a little nervous about releasing model run results before there's been a proper political debate associated with them, so I'm on a short leash in this regard, and I can really only show some sort of demonstration policy tests at this point. Looking at a base case versus playing with increasing the cost of travel, increasing the time it takes to travel, removing the truck route restrictions completely, and then a large toll for trucks going into and making stops in the central business district. And this just shows the sorts of changes then we get. This is in the vehicle kilometers, VMT, sorry, that vehicle kilometers traveled in Calgary, but it's the same thing as vehicle miles traveled here. All right. And you can see I've got a base primed. What I'm doing over there is just sort of, let's rerun the base again and see what sort of drift we have in this value just because of the microsimulation random component to it. And you can see we're very, very close when we look at base primed as opposed to base, which is 100%. All right. But you can see in all cases those things reduced the vehicle kilometers traveled for increasing the cost, increasing the time, and having no truck routes. But the toll ended up increasing things because they had to avoid the CBD to some extent then. Then looking at the numbers of tours, trips, and total vehicle kilometers traveled change when we go to the no truck routes. So let's open up the truck route policy and allow any truck to go anywhere. The commercial vehicle allocations can now be a bit more efficient than they used to be. And they can get away with less tours, less trips per tour, and a reduction in the total vehicle kilometers traveled. All right? So the truck route policy is nice. We can then exclude those larger vehicles from certain areas, but it has a cost to society. And that cost is we actually end up forcing them on more circuitous routes at times, and there's a total vehicle miles traveled increase as a result of that. They can make that trade-off if they want. The model is just informing that decision. What's also interesting is, of course, it has a differential impact for the different types of vehicles. This is one of the great powers you have with the microsimulation process is you can slice and dice your results any way you want afterwards. You can add up what's happening to vehicles that are providing services, or you can add up what's happening to light vehicles, because you've got sort of a data set at the end of all of the results for that full set of vehicles that's been microsimulated. So in this case, what you're seeing happening here is when we removed the truck route restrictions, light vehicles lost their competitive advantage. They used to be able to go everywhere in a way that the medium and heavy couldn't. Now that the medium and heavy can also do that, there's a drop in the use of light vehicles. There's a shift back to larger loads that are more efficient. Medium vehicles, they still also tend, they don't do quite as well. The heavy vehicles actually enjoy an increase in use, as you would expect. Right? So the model was doing something we felt was sensible in terms of that policy test. So what are some conclusions then I can offer from all of this? We'd say we've got a successful application of this commercial tour-based microsimulation. It provides a direct, explicit representation of the trip chaining and the impacts of trip chaining. We don't have to represent empty vehicles anywhere. That's a great thing you wrestle with more aggregate approaches in commercial movement modeling. And there's lots of papers in the literature trying to wrestle with how to handle empty vehicles, because they don't make sense in and of their own to be moved around. They're part of larger tours that have to be made, and you've got to get the trucks back. Okay? But because we're dealing with this explicitly, the idea of having a tour and going back to the establishment, we sort of naturally have solved that particular problem. We don't really get into whether they're less than load or full load or light. We just have the patterns that the vehicles tend to make out in tours. We've got service delivery included as a fairly, and they're a large sector of the total, So this is well beyond the freight only and the large truck only limitations of some previous work. We'd argue we have a useful planning tool. All right. They now use that in the city of Calgary. They include commercial movements with this component of their larger model, right? And they are able to take into account the impacts of commercial movements and what the benefits are to industries using producer surplus calculations as part of their evaluation of policy. The microsimulation process was fairly stable. We found a way to integrate it with an aggregate equilibrium model using that parallel process and a number of runs and averaging. We like the success, or the tour growing rather than rubber banding in this context. I think the rubber banding makes more sense on the household context. But in this case, where we had a different kind of tour, much larger tours with more stops, we liked the flexibility, the added advantage we had of the growing representation. We've got transport and handling represented as a service in the way that I described. Right? It's part of the total commercial movements that are going on. I won't go into the details about, we actually had two ways of estimating the transport and handling movements. One is the demands arising, and the other is what's provided in supply. And we had a way to check our expansion because we were getting similar values for those two different estimates. Successful integration, all right, of truck route compliance within our path choice, that path choice simulation process. We hadn't seen that in the literature anywhere, so we're pleased. We think we have something that's worked in that regard. The data were extremely important in this. Really, there's comparatively little known about commercial movements. They are only 12 to 15% of the total that's going on in an urban area. So in some sense, it's a straightforward decision to ignore it or to treat it rather cursory. But they have very differential impacts. That 12% of vehicles, some of them are very large, and they're very concentrated in certain areas. So we think it's a stronger model when we have them represented explicitly in the way we're representing here, even though they are only 12%. There's not a lot of work that's been done, and there's few sort of rules of thumb out there. We don't have the same sense of what works and what doesn't work, what to expect, that we do on the household side. So collecting the data that we went out and did, that $1.5 million spent in the two cities with the province supporting it was very well invested, I would argue, but I suppose I would say that. The logit choice models, they provided a lot of very interesting insights into the nature of commercial movements that we haven't seen anywhere before. So we'd argue that it was worth the expense. So the stop duration model, that's the weakest part. We have been working on hazard duration forms of that. They're being put in now, but we aren't using it in any policy work yet. It's still just the sampling distributions at this point. And we are eventually going to fit it in as part of an input-output, spatially disaggregated input-output model. So I think we can leave it there and throw open for some questions.
And I want to remind people to use the microphone in front of you. Hopefully there is one before you ask a question.
Go ahead.
Yeah, I was curious if you were able to calculate the number of commercial tours within Calgary that originated outside of the study area, and if this was significant, what kind of considerations or assumptions were made in the model for
Good question. Okay. First of all, we have the city itself, then we have our model area stretches out about 60 to 70 kilometers in each direction. So there's a large sort of what we call regional component to the model. And that's still modeled in the same sort of way. The issue, that really just pushes your question to a much more further edge. But, but your question is still valid. What we did on the edge is we went out and collected data by stopping trucks in a external cordon. There we only stopped trucks. We didn't stop private vehicles as well. So there we are limited to only knowing what's happening on those medium and heavy vehicles rather than all vehicles. It's very tough. When you're standing at the side of the road, on a freeway, and there's a light vehicle going by, you don't know if that's a commercial or a household movement. It's very high likelihood it's actually a household movement. But you don't know till you stop them. Whereas when you see trucks going by, it's pretty certain it's a commercial movement. So we got permission to stop the trucks. We didn't have permission to stop the vehicles, the light vehicles. So we had to sort of make do with what we call an external to internal matrix for those movements, just for the light and just for the medium and heavy trucks. The light vehicles we have in a separate part of the household model is where we handle that. So the next thing to appreciate is that both Calgary and Edmonton are fairly large centers with very large hinterlands out from them, where there's a large agricultural base that's bringing things in. So we don't really have a large integrated manufacturing economy like you might have in, say, for example, Ohio or New Jersey, where you would expect very large numbers of trucks going external to external. We had a very, very small number of trucks. The order of 2 to 3% were actually external to external. Most of them are coming in and stopping. I mean, it's sort of a long way from Vancouver to Calgary and then Calgary to Regina. All right, those tend to be sort of entire days for trucking movement. All right, so that you see very few truck movements going right through the city. Okay, so our external to internal model pretty well picked everything up. We didn't need very much of it. It's a very, very cursory external to external, and we freightar it up just consistent with what we're expecting the totals to be. And all the action happens inside with the microsimulation we're describing. We don't think there are very many service trips that leave that 70-kilometer boundary, right? They tend to be very much focused in. So we're compromising a bit, but we think it's well within sort of what would be a practical sort of compromise. Is that? Yep.
The City of Portland is currently doing a freight master plan, and they seem to be very much using the word freight as opposed to movement of goods and services. Would you suggest that that distinction will distort policy choices, or does it lump together well?
Oh, that's a loaded question, isn't it? I think there's a serious shortcoming to a study that only looks at freight and doesn't pick up the movement of service, and one that only, I don't know how they're handling trucking companies, whether they're including them as freight, which, I mean, you see, in economic statistics, that would be a service, not a movement of a good. So I don't know, but I expect they are probably including that. They're probably getting about 2/3 of what's going on the commercial movement side in total. They're probably getting a lot of what the trucks are doing, but there's a lot of commercial movements in light vehicles and delivery of services in small vans that they aren't getting at all.
The trucking lobby is very politically powerful here.
Absolutely, absolutely. And I've had this presentation where I've said these are commercial movements, and then people get up, but the important commercial movements are the trucks. But that's a lobby group that has that particular perspective. So, again, 60% of commercial movements occur in light vehicles. 2/3 of them are the delivery of services, right? 1/3 services, 1/3 own account goods, and 1/3 trucking movements.
Do you have any sense of how that, if that's 2/3 of the trips, do you have any sense of how that breaks out the economic value?
You mean in terms of the values that are being shipped? We tried to collect value in the data where we asked, and that was really tough. A lot of the drivers that we were asking the questions of on the loading docks had no idea. Look, mate, it's just stuff, man. I don't know what it's worth. There's probably a better answer to your question associated with looking at input-output structures and what are the values of the commodities that are being shipped around. And, it's increasingly services in an urban, Western developed country urban economy. More and more emphasis, there's less and less emphasis on the goods themselves. So they're representing smaller and smaller proportions of the total. But I can't give you exact numbers, especially not from the context of the data we collected here. We tried values, and then we set some poor guy trying to impute values where we didn't get them, and eventually we punted on that.
Actually, I have a follow-up question about data. How difficult was it to compile the data for this?
There was a lot of cooperation from the firms. When we started out, there was a lot of nervousness. Oh, they're not going to be as cooperative as households because there's a competition element to what's going on here. To what extent are we getting into trade secrets and proprietary information? We went to the trucking associations, and the trucking association. There's 2 trucking associations in Alberta, and we also went to the chambers of commerce in the 2 cities, and we got endorsements and got their. We had sort of working group meetings that included these guys, and we kept explaining, that the extent to which we get good information here, we're going to be able to plan a system that benefits the business community. In a way we haven't before, because before it's just all focused on households. And they've been out to public meetings where they got their chance to say something, but really a lot of the analysis had already supported a household associated view of things. And they were finding more and more truck routes, more and more restrictions on what they could do. So this really pushed a button for them, that this was their chance, an entree. And they got pretty good at putting in their association newsletters. There's a network out there. These guys do talk. And a lot of them are small firms, in fact. They worked pretty hard. We had a media blitz. And we did reasonably well, I thought. We got sampling rates that would be similar to household sampling. We had lots of refusals still. But, we got 35% of the firms agreeing to participate in this thing and giving us a lot of information that they understood was confidential, but we had the same sort of privacy, rules that we were applying to households. We made the same declarations on the commercial side, and we said we would respect their privacy. We're using it for this particular purpose. We're not going to sell it to somebody else. We had to sign understandings to that effect. So we did get, I thought, reasonably good cooperation. It was much better than we worried about initially. There was a cynical view that we wouldn't get much cooperation at all, but it worked. We have also done this in Ohio. We've collected the data, and we had very similar experiences there. So this was something that at least translated from the Western Canadian cultural context to a Midwestern context in Ohio. There was when we were doing it in Ohio, there was a lot of nervousness. Oh yeah, well, maybe the Canadians will participate, but people in Ohio won't. They did. I think you can go to the well only so many times. If you go out and you build up a lot of expectation, and then you don't build your model and they don't see anything as a result of it, then I think going back the second time's a lot tougher. But I think there is some goodwill that's out there, and there is some concern that they'd like to be represented more completely than they are right now within the sort of the urban decision-making context and the tools that are available. So I think there is scope for getting them to participate. So.
Okay. I'm just going to conclude here. I want to thank you. Before we officially thank you, I do also want to announce this Friday's seminar, which is the start of our regular Friday seminar. And we'll be having Professor Stephen Ficus from University of Oregon talking about the GO project, helping people access their community through assistive technology. Should be quite interesting. And without further ado, I want to thank Doug Hunt.
Okay, thank you.